Hi, we are this year's capstone team for Monterey Bay Research Institute's MBGRD to GLTF file converter project. I am Eric Rios.
I'm Miguel Gonzalez.
I am Jonathan Ramirez.
I'm Dan Mazende.
And without further ado, we'd like to walk you through our capstone project.
So a quick overview on this project. So this project, we use a tool called the MBGRD2GLTF. And what this tool basically does is it'll grab a GRD file from the MBARI aquatic machines. It'll grab their data and then it'll then convert them into a GLTF file, which we can then view in a different 3D software system. This tool was originally created by MBARI and has since been updated by different CSUMB students through multiple iterations of capstone projects.
We had three main goals we aimed to accomplish for this capstone project. First was to provide support for all GRD format conventions such as GMT, COARDS, CF, NetCDF, and so on. These files are essentially grid file formats used to store mapping data. The current converter lacked full support for each of these formats. Second was to fix export compatibility issues that arose when attempting to view the converted GLTF files in third-party viewers such as Cesium and Babylon. And last was to take the MBGRD to GLTF code and standardize it. As this had been an ongoing project for various capstone teams, there was no standard coding convention that the project really adhered to.
So some of the errors we were facing when viewing GRD to GLTF outputs was we were generating invalid meshes. What a valid mesh must have is a matching vertex count, a correct and complete index buffer, and attribute layouts that are consistent across all vertices. The reason for this is if there's any discrepancies within it, it'll fail. So for example, with the Draco compression, Draco is our primary mesh compression method used by MB systems internally to reduce file size. So what it is expecting, it is a valid mesh. But when XY size is wrong, the arrays become unrealistically large. So it just spits out a random number, causing Draco to fail. When Draco fails, the tool automatically switches to the fallback encoding. Within our fallback encoding, what it does, it just writes the raw uncompressed mesh data into the GLB. But since those are hard-coded within the fallback errors, it is just spitting out random information. So when putting them in a viewer, it doesn't let you view it. So also with the Draco compression, even though it goes through, some GLTF viewers don't support the Draco decoding. Those viewers, they rely on the fallback mesh to display the model. If the fallback path produces invalid buffers, it'll just call it corrupt. It's made up data, so it doesn't output anything. So all of the GLTF failures we just covered ultimately come from one issue, the grid dimension being interpreted incorrectly. The netcdf files don't use a consistent schema. Some files, they just use single XY size, while others use X and Y, along with strings as well, like longitude and latitude, or shortened lan and lat. Any mismatch causes it to not produce properly. The fix was switching to dynamic dimension detection. Instead of guessing which dimension represents the grid, the constructor now probes the file. It checks for MB system XY size, then GMT, etc., etc. It then verifies that the dimension sizes actually align with the elevation variables before accepting them. This gives us a stable XY size, and it allows us to support GMT, MV systems, CF, and COARDS without any special cases. Fixing the stage is what prevents the malformed meshes we saw earlier, because when dimensions are correct, both Draco and the fallback encoders finally receive valid geometry. So in that valid geometry, here we could see in Lake Erie now being produced, Lake Michigan, along with San Pedro Basin.
We tested our GLTF output using third-party visualization tools and identified some structural issues in the configuration. We focused on integrating our bathymetry visualizations using cesium, and we were aiming for wide adoption through web browser accessibility rather than native desktop tools.
Some of the main issues we're running into when viewing the GLTF files and other softwares were array length and abort errors. So what these errors are is basically saying that the data in each file was either too big or incomplete to be generated. And basically what we did to combat all these errors was we generate the model in multiple smaller grids instead of one giant grid. We can still generate the whole model, but it is just generated in chunks. But by doing this, we are able to reduce the chance of any data loss happening, as well as being able to still generate really big heaps of data in a timely manner.
So the approach we took to standardize the code within the GRD2GLTF tool was to introduce a claim format configuration using LLVM base, loosely inspired by Google Style Guide. This gave us a clean, consistent baseline while still respecting the structure of the legacy code. The reason for this was because the project has evolved across multiple capstone teams, each with their own formatting coding habits. We wanted to avoid enforcing a strict style guide that might disrupt the existing logic or introduce large diffs. As it is now, the formatter simply provides a safe cleanup that improves readability. And that's it for our capstone presentation. And as an aside, we'd like to give a special thanks to our mentor for this capstone project, Mike.
Thank you, Mike.
Thank you, Mike.
Thank you, Mike.